Right now, at this exact moment, a fragment of primordial ice is hurtling away from our planet at 137,000 miles per hour. It has already made its closest approach to the Sun, swung past Earth at a distance of 168 million miles, and is now vanishing back into the darkness between stars. But here's the part that doesn't make sense. The frozen chemistry locked inside this visitor predates our entire solar system by more than 6 billion years. I'm Arif Hassan, and if you want to understand why two of the most powerful observatories ever built, James Webb and the Vera Rubin Observatory, just independently confirmed the same object, and what that means for our place in the cosmos, hit follow now. By the end of this video, you'll understand exactly why scientists aren't calling this a threat, but are still describing what they found as genuinely terrifying. The story begins on July 1st, 2025, at the Asteroid Terrestrial Impact Last Alert System facility in Rio Hurtado, Chile. ATLAS, as it's known, is designed to scan the sky for fast-moving objects that might pose an impact risk to Earth. That morning, its cameras picked up a faint point of light drifting through the inner solar system. At first, it received the standard provisional designation C/2025N1. But within days, orbital calculations revealed something far more significant. The object's trajectory was hyperbolic. Its path was so open, so sharply curved, that it could not have originated anywhere in our solar system. It had come from interstellar space. Astronomers redesignated it 3I/Atlas, making it only the third confirmed interstellar object ever detected by human beings, following Oumuamua in 2017 and 2I/Borisov in 2019. Both of those earlier visitors were fleeting encounters, offering only weeks of observation before they faded into the void. 3I/Atlas would turn out to be different. Almost immediately, observatories across the planet reoriented their schedules. Yet the most remarkable early data didn't come from a targeted observation at all. It came from an accident. The Vera C. Rubin Observatory sits nearly 2,700 meters above sea level on Cerro Pachón, also in Chile. Its primary mirror spans 8.4 meters, wide enough to park a city bus across, and its LSST camera captures 3,200 megapixels in a single frame, roughly 200 times the resolution of a typical high-end smartphone camera, making it the largest digital camera ever constructed for astronomy. In mid-2025, Rubin was not yet conducting its official survey. The telescope was in a commissioning phase called science validation, essentially a final systems check before its decade-long legacy survey of space and time began. Engineers pointed it at various patches of sky to test focus, calibration, and software pipelines. They were not hunting for interstellar comets. They were simply making sure the machine worked. Weeks after Atlas announced the discovery of 3I/Atlas, a team led by astronomer Colin Orion Chandler decided to comb through Rubin's archived validation images. They weren't expecting to find anything. But on June 21st, 2025, 10 full days before the rest of the world knew this object existed, Rubin had already recorded it. The interstellar visitor was sitting quietly in the background of routine calibration frames, completely unnoticed at the time. The telescope continued to image it, entirely by chance, through July 20th, collecting nearly 100 exposures. 49 of those frames would eventually form the basis of a formal scientific study. What those accidental photographs revealed was striking. The object displayed a developing coma, a hazy envelope of gas and dust surrounding its solid nucleus. As 3I/Atlas drew nearer to the Sun, that coma swelled by over 50%, which is exactly what you'd expect from a comet heating up. But one detail caught researchers off guard. The dust tail wasn't pointing away from the Sun, it was angled toward it. Under ordinary conditions, solar radiation pressure pushes a comet's dust tail outward, away from our star. A tail facing sunward is rare, though not without precedent. Astronomers attribute the effect to anisotropic dust emission. Essentially, the nucleus was venting material unevenly across its surface, creating a jet that, from our specific viewing angle, appeared to defy the usual geometry. It was an oddity, certainly, but it was physics, not a mystery. To appreciate how Rubin caught this, consider the precision involved. The observatory images the sky through 6 filters, designated U, G, R, I, Z, and Y, spanning different wavelengths from ultraviolet to near-infrared. Chandler's team measured 3I/Atlas across all 6 bands with a positional accuracy of roughly 70 milliarcseconds. For context, Rubin can pin stationary background stars down to about 3 milliarcseconds. The slightly looser tracking on 3I/Atlas simply reflects the difficulty of locking onto something that is actively moving against the stellar backdrop while still being incredibly faint. Over 300 collaborating scientists contributed to the resulting paper, analyzing astrometry, brightness curves, and morphological changes entirely from these unintentional early images. But here is where the story pivots. Rubin gave us the shape, the timing, and the motion. What it could not give us was the object's origin story. For that, astronomers turned to a completely different kind of telescope, operating from a place where Earth's atmosphere can't interfere with the data. On August 6, 2025, the James Webb Space Telescope aimed its near-infrared spectrograph, or NIRSpec, at 3I/Atlas. Webb orbits roughly 1.5 million kilometers from Earth at the second Lagrange point, shielded from our planet's thermal noise. Its instruments are designed not to take pretty pictures, but to dissect light into its constituent wavelengths, to read the chemical fingerprint of whatever they observe. Webb's first pass detected carbon dioxide, water vapor, water ice, carbon monoxide, and carbonyl sulfide in the coma. On the surface, these are familiar cometary ingredients. But the ratio of carbon dioxide to water was unlike anything ever cataloged in any comet, whether native to our solar system or visiting from beyond it. That ratio is not a random number. It encodes the temperature, pressure, and radiation environment present when the object formed. A higher CO2 to water ratio suggests formation in a colder, more distant region than the comets we have studied around our own sun. If confirmed in future interstellar visitors, this pattern could mean that comets forming around other stars routinely develop with chemistry radically different from our own local examples. Then, on December 22, 2025, Webb observed the object again. By this point, 3I/Atlas had reached perihelion, its closest approach to the Sun, on October 29th, and had swung past Earth on December 19th at that 168 million mile distance. The increased solar heating had turned the comet into a far more active target, perfect for deeper spectroscopy. This time, NIRSpec measured isotope ratios, specifically the proportion of deuterium, or heavy hydrogen, relative to ordinary hydrogen locked in the ice. Those isotope ratios did not match a single known comet from our solar system, not one. Working backward from that chemical signature, researchers calculated that the ice inside 3I/Atlas likely condensed between 10 and 12 billion years ago. Our Sun and its planets did not even begin coalescing until 4.6 billion years ago. That means this object was already a frozen, finished artifact drifting through the galaxy for billions of years before the cloud that would become our solar system had even started collapsing. Some researchers have noted that places this comet's formation in the early Milky Way during an epoch when our galaxy was still assembling its spiral structure and the universe itself was less than 4 billion years old. The paper presenting these findings was published in the journal Nature on June 22, 2026, following full peer review. So let's address the question the title raised. Is this object terrifying because it poses some kind of danger? Absolutely not. At its nearest, it remained more than 168 million miles away, roughly twice the distance from Earth to the Sun, and its trajectory follows gravitational physics with no anomalous deviations. It is not an artificial structure, it is not a probe. Every measurement, from Rubin's astrometry to Webb's molecular analysis, points to a completely natural comet made of ordinary ice, gas, and dust. But here is why the word terrifying still fits. This object is a frozen time capsule from a version of our galaxy that no human telescope has ever directly witnessed. The deuterium ratios act like a chemical clock, and that clock tells us the material inside 3I/Atlas formed in an environment with a fundamentally different chemistry than anything in our solar neighborhood. It is older than our Sun, older than Earth, older than every planet and asteroid we have ever touched or photographed. It is a physical sample from another era of the Milky Way that just happened to pass close enough for us to study. Holding that thought for a moment, consider what it means. We are not just looking at a comet. We are looking at the chemistry of a place and time so remote that our own star had not yet ignited. Consider the comparison to our previous interstellar visitors. Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii, was elongated and showed a slight, unexplained acceleration as it exited our system, likely outgassing that was too faint to resolve directly. Borisov, discovered in 2019 by an amateur astronomer in Crimea, looked and behaved much more like a typical comet. 3I/Atlas is different from both. Its orbital eccentricity of approximately 6.14 is dramatically higher than either predecessor, confirming it was never even briefly captured by our Sun's gravity. At 137,000 miles per hour, it is moving fast enough to cross the entire continental United States in under 90 seconds. Researchers estimate its kinematic age, the time it is likely spent drifting between stars, at somewhere between 3 and 11 billion years, a range that overlaps neatly with the separate chemical age derived from Webb's spectroscopy. Hubble observations place the solid nucleus somewhere between 440 meters and 5.6 kilometers across. That wide uncertainty exists because the bright coma obscures the true edges of the core, a common challenge with active comets. Meanwhile, NASA's SphereX mission detected infrared signatures of dust, water, organics, and carbon dioxide using an entirely different wavelength range than Webb, adding an independent layer of confirmation. NASA's TESS mission, normally busy hunting for exoplanets, was redirected to monitor the comet's rotation and activity. Even the European Space Agency's JWST spacecraft, en route to Jupiter, managed to snap an image during its own cruise. In total, 3I/Atlas became one of the most extensively studied interstellar objects in history. And that brings us back to why the dual confirmation from Rubin and Webb matters so deeply. These two observatories represent opposite but complementary strategies for exploring the universe. Rubin is built for breadth. Its entire purpose is to scan enormous swaths of sky repeatedly, catching transient objects simply because it is always looking. It found 3I/Atlas by accident in test data before anyone knew to search for it. Webb is built for depth. It stares at single targets with crushing precision, pulling apart light to reveal molecular and isotopic details that ground-based telescopes cannot access. Rubin answered when and where. Webb answered what and how old. Neither answer would carry full weight without the other. Rubin's early timeline proved the object was already active and measurable before official discovery. Webb's chemistry proved its materials were forged in a distant, ancient environment beyond our solar system. Together, they constructed a complete biography of a traveler that has been cruising through interstellar space since long before our planet had oceans. This is the larger implication. Our galaxy has been producing and ejecting comets for most of the universe's 13.8 billion-year history. Our solar system is a relative newcomer. Objects like 3I/Atlas suggest the Milky Way is littered with ancient, frozen debris from epochs we can never visit directly. Every so often, one drifts through our neighborhood. If we have the right instruments running at the right moment, we get to read its diary. Right now, 3I/Atlas is fading. It has crossed the threshold where most telescopes can no longer track it effectively, returning to the same cold, dark medium it emerged from. It will likely never pass another star as closely as it just passed our Sun. The data gathered by Rubin, Webb, Hubble, and the others now exists as a permanent record. A snapshot of an object born in the early galaxy, captured during a brief, accidental encounter with a species that didn't exist when the comet formed. If you want to keep seeing fact-checked deep dives like this every time a genuine discovery breaks in space, subscribe now and turn on notifications. Drop a comment and tell me which detail stunned you more. That Rubin photographed this thing 10 days early by pure chance? That its tail pointed toward the sun? Or that the ice inside it is older than our entire solar system? Share this with anyone who needs a reminder of how strange and old the universe really is. Thanks for watching all the way through. I will see you in the next one.